Good morning. Welcome to part 2 of 3D printers and pyramids. What do they have in common? Today, I'm going to go back about 4,500 years and look at the tools that the ancient Egyptians used to solve the problems of creating the Great Pyramids. Those tools turn out to have similar functions and amazing accuracy in some cases that relate directly to the construction of modern machine tools like 3D printers, milling machines, laser cutters, etc. So without further ado, let's see what we have. First of all, I've gone back and using historical or archaeological sources made some replicas of some of the simple tools that the surveyors and builders used to lay out and cut the stones used to assemble the pyramids. I'm not going to deal with the problems of moving the stones from a distance and then stacking them up into a 450 foot high pyramid. We're just going to address how did they lay it out and how were the stones prepared for use so that they would fit. There are basically only 6 steps that we're going to address today. First, probably needed a plan. And they had to plan for a square base, which was level and flat, 2 different things, to provide a solid foundation. Now, they had some prior experience with some earlier pyramids that, surprisingly enough, didn't quite turn out so well. In fact, there's one called the Bent Pyramid. And they had some foundation problems. But on the Great Pyramids, they seemingly perfected their procedures. Second, you had to lay out the base that, if you're going to make a square pyramid, that was square with 90-degree corners. Okay? And the links had to be established. Third, you had to remove the sand that overlaid the bedrock and actually level the base. Fourth, you had to actually cut the rectangular stone blocks so they would fit closely together. And fifth, you had to finish the facing stones, not rectangular, but with a precise angle to cover the stepwise stones that were laid up. And that angle was 51.5 degrees approximately for all 4 faces of the pyramid. And then you had to maintain that consistent angle for each, on the 6th step, for each of the 210 layers that you're using to build the pyramid. Well, before we get started building, we're going to go over just 2 definitions. The first is the definition that I find most interesting for level, and that is, it can be defined as a surface that's conforming to the liquid parts of the Earth's surface. That's going to be important for one of the tools we'll look at in just a moment. And then secondly, we're going to define flat using a modern definition in machine tool building as 2 sets of parallel lines, 2 sets of parallel planes where the reference, within which a reference plane must lie. So for example, if I take 2 index cards, these would be parallel planes, and if they're close together, a flat surface would fit between them. But for example, if I try to fit a curved surface between 2 flat planes, it's not going to fit. Anyway, the closer the reference planes are, the higher the tolerance. And the interesting thing about the Great Pyramid is that it is flat over an area of about 750 feet on a side. It is a square 750 feet on a side to 2.1 centimeters, or about 8/10 of an inch. So if you can imagine, that's pretty flat even in today's construction technology. The first building method we'll look at is leveling with the aid of water. And I've prepared a base here that's supposed to represent what happens if you remove sand and are left with some bedrock. Well, the bedrock is not perfectly flat, and you can see various lumps and depressions throughout it. And I've also dug some trenches around the perimeter that's supposed to represent approximately the size of the base of the pyramid. And while there's some speculation as to exactly how they did this, water leveling is one approach. So I'm going to put some water in here, and what you will see is that the water forms its own level, and you can take a chisel and knock off the high spots. Now the water is soaking in here, but when you have a network of channels and you continue to fill those up, and I'll fill it up a little more here, you can see the high spots that are clearly able to be knocked off one at a time. And as the water level goes down, different high spots show up, and you can continue that iterative process until you have a base that's flat, in this case flat to less than one inch. The next step is to lay out the first of our baselines. These are going to be about 750 feet long, and to do that you need some kind of consistent measurement. The Egyptians used what we call a cubit, and this piece of wood is approximately as long as what was called the royal cubit, and it's subdivided with a number of smaller markings, and let me show you what they are. This marking here is 1 digit. That's 4 digits or 1 palm, so you have multiple palms, and there's a total of 28 digits in the cubit. Each of the digits then could be subdivided into 2, 3, 4, 5, 6, etc., up to as many as 16 subdivisions for fractional parts of digit. This was used both to set the lengths of rope with knotted rope, so they could stretch a length of rope between 2 points and use that to lay out the line. However, over 750 feet, the rope would sag, so you would have to use multiple rope pullings. In fact, they had a term for pulling ropes to set lines with sight lines using another instrument that we will talk about in just a second. So you have a cubit to establish the basic length, and this is essentially the length from your elbow to the tip of your outstretched middle finger. So that's the cubit, and then you have to establish a sight line so the line doesn't waver. And one of the devices that they had, and this was used by both the Egyptians and then later by the Romans to establish streets, military encampments, and basically the entire Roman Empire. And what it is called a Groma. Let me move this out of the way. It's called a Groma, and it allows you to use these 2 plumb lines, and it's just a weight on a string. The top has a 90-degree angle, so that these strings going this way are exactly 90 degrees to these strings going this way. But for the purposes of laying out one line, all you have to do is sight so that one line coincides with the other, and then you have a person standing at a far distance, the line that you want to survey or lay out, that holds a stick vertical, and you can make the stick vertical with another plumb line. And when those lines line up with the stick, you know you've got a straight line between those 2 points, and you can put markers or poles along that to guide the folks who are going to be digging or laying the stones. So that's the Groma, one way to establish lines, but you'll notice that it already requires 2 sticks at 90-degree angles. Well, how did they come up with 90 degrees or square angles that are going to be now used? Once we have one line, we've got to establish that second line exactly at 90 degrees. Well, they have another, I guess we'll call it an invention. If we look over here, we see a piece of rope with some knots in it. And it turns out that the Egyptians knew that a triangle that had 3 units on one side, 4 units on the other, and 5 units on the third, or the hypotenuse, would always form a 90-degree angle at the base. So that was another way that they could establish 2 lines at right angles to one another, and therefore get a perfectly square corner. Now, of course, a longer rope with knots every cubit could be used to measure longer straight line distances. Now, one final method that may have been used by the Egyptians was simple geometry, and you're probably familiar with the process of bisecting a line. So let's get this straightened around here. If this is our first straight line, and imagine this is 750 feet long, and you want to make a square corner, well, what you do is draw another line 90 degrees to the first, and the way you can do that, I want to make sure it shows up, is you put a rope with a length more than half the distance up here, and you put a stick on the other end of the rope, and you rotate it on one side, put the same length of rope, the same stick over here, rotate it on this side. Where it intersects, you make a mark, and then you do the same thing on this side, put the same stick with the same length rope. Basically, you've got a compass now. Mark it off, put it up here, mark it off, and now when you connect these 2 lines, again using your sighting mechanism that we just discussed, you'll have a very accurate 90-degree corner. So the last part of our plan, before we actually start cutting and getting our stones ready, is to establish the angle of the slope. And I've drawn in the actual angle, which is, I said, about between 52 and 53 degrees for the Great Pyramid. I'm sorry, 51.5 for the Great Pyramid. And the way to do that, the way they did it, is to take 1, 2, 3, 4, 5 palms and 2 digits. Their method of measuring or creating angles was to use a ratio of the number of palms and digits to a whole cubit. And let me back up a little bit so you can see the whole layout. I've made a triangle with the 51.5 degrees. It's 1 cubit high, and it's more or less exactly 1, 2, 3, 4, 5, and 2 digits for the base. And that gives the angle that they can check as they're building up each of the 210 layers. Now, for leveling and checking angles over short distances, the Egyptians had their own style of level that was actually used for thousands of years, which is formed by making a triangle an isosceles triangle with two equal sides with a plumb bob hanging from the center. And when you have a level surface, you make a mark, or you have an index at the exact center. Let me move that in closer so you can see. You can see there are several marks on here, and those marks would correspond, the center one would be 0 angle. This particular mark would represent this side being at a 51.5 degree angle, so that it can be used to check progress as you're building things, and even assist in cutting the stones. Now, the problem, of course, is how do you construct a 90 degree angle when you don't have one? Well, this particular one I constructed by measuring a 3, 4, 5 triangle distance by taking a 3 on one side, a 4 on the other, and moving these apart until the distance became 5, and that gave me a 90 degree angle at the apex. So you can see, if the device is not perfectly level, this plumb bob is going to move to one side. If it's high on that side, it's going to go here. And if you're chopping stone and so forth, you can chop the stone off on one side until it's leveled up. While the base of the pyramid could be flattened and leveled using the water level that we discussed earlier, when it came time to flatten the sides of the rectangular blocks, which were each 3 or 4 feet long, used to assemble the pyramid, a different method, or several different methods, were employed. The first one was using 3 identical height blocks. In this case, I'm using 3 Lego bricks connected by a rope or a string. And as you can see, I'm going to slide these 2 bricks across the table, and you can see it just touches the top of the one in the middle, which is what you would expect if the tabletop is flat. However, I've taped a piece of paper here, and that would represent a high spot, and so I want to be able to detect those high spots. And you can see that as I sweep the string across, it touches the top of the block, and all I need to do is mark that, and then go through with my hammer and chisel and knock that spot off, and thereby achieving a very flat surface all the way across, simply by sweeping all the way at different angles across the block, until you've achieved a surface that's flat enough so that these blocks, when placed adjacent to one another, would not leave too large a gap. Make it even flatter. And let me prepare this example before we go on to the next step. Now, this is how you prepare stones so that they will fit together so tightly that the pyramid will last for thousands and thousands of years. It also is a direct antecedent to, or predecessor to, the methods used to prepare flat objects even today in the machine tool industry. So what I've done is taken a flat plate here and coated it with red paint, and the Egyptians apparently used red paint for theirs. And I take one flat object and I rub it across this rough rock, and let's see what it looks like. Okay, if you look carefully, you can see that there are 1, 2, several over here, and another here. These are high spots. So I take my chisel. In their case, they would have used either a copper chisel or various kinds of hard stone chisels and hammers and knock these high spots down. 1, 2, 3, 4 high spots, but nothing else is marked. And now when those high spots are knocked off, you repeat the process, rub it, and you're going to get different high spots. You knock those down. And you keep repeating that until there are red marks, not just on high spots, but all the way across the rock. And now you know you've got an absolutely flat surface. You turn the rock on its side, you flatten that surface. Okay, now, you may have noticed that I started with a flat sheet. Well, how in the heck did the ancient Egyptians make the first flat sheet? It's kind of the classic chicken and the egg. Well, let me show you the basic method on how they did that. What we have here is 2 small discs. In this case, instead of rock, I'm using plaster of Paris because it's softer and easier to work with. And all you need to do is to rub them past each other with a motion back and forth. You turn each one back and forth. And if you're using rock, it takes a long time. And in fact, you could put harder sand material between it to speed up the abrasion. But you rub one surface against another, and if you rotate them and keep rubbing in a fairly random fashion, the top surface will take on a curve on the underside, a concave curve. The bottom surface will take a convex surface. So what you have, if you keep doing that, you'll get more and more curved rocks. But what you want is a flat rock. So what you do is flip them over. You put the top one on the bottom on the top, and you repeat that process. And now you'll get 2 surfaces that mate perfectly, but they'll be flattened out. Later revisions to this process are what in fact are used today to create the flattest possible surfaces down to the millionths of an inch. But to do that actually requires 3 blocks. So you start with 3 blocks and you interchange them so they mate with each other. Then you bring a 3rd one in, rub that back and forth until it matches it, and then reverse the keep exchanging them. And the bottom line is, eventually you get 3 perfectly flat rocks, or pieces of cast iron, or glass, and so forth. This process turned out to be very important in later inventions like eyeglasses. This is how glass is ground for eyeglasses, and how mirrors are ground for telescopes. Even today, this process is used to create perfect optical surfaces for various kinds of tests and measurements. So once we think that our building stones are flat enough, we have one final check we can make. And we can take one flat object. I'm not going to use the one with paint on it right now because it's messy, but let's assume that this piece of wood has been flattened using the procedures we talked about, and then sight along that across the surface and see if we see any light coming through and gaps. And you can see this has high spots and low spots because it's not yet been flattened. If we had gone through the whole process and rubbed this stone against the second stone, we would have established a flat plane within a high degree of tolerance, and we wouldn't be able to see any light. And so that's kind of the final test, and one we'll be using in a few minutes on testing our 3D printer components. So without further ado, let's switch to the modern implements that are used to create 3D printers and test them for accuracy. I'm going to now take a look at some modern tools that can generate the accuracy needed to make and test a 3D printer, or really any other complicated machine that requires close precision. The foundation, just as in the pyramids, is flatness. And for that, the key tool is something called a surface plate. This is a small one. It's made out of granite, and the top has been flattened to a few 10,000ths of an inch across the surface. So it's a very flat surface that is going to be the reference for essentially all of our other measurements. Okay, so that's flatness. We'll see how to use it in a few minutes. Second is a standard of length. Just as in the Egyptians, where they use the cubit, we need as their standard. We have various standards of length, all based on the metric system. I have an example here that's measured in inches, and this is called a gauge block, and it's exactly 1 inch thick, plus or minus a few millionths of an inch. And these gauge blocks come in various sizes. Here's a 1/2 inch one, and if I want to have a standard measurement of exactly 1.5 inch, all I have to do is what's called ringing them together, and I stack them up, and now I have an item that's exactly 1.5 inches that's going to be more precise than some other measures that we might use, like a ruler for length. It's very simple. A more precise version of that is called a micrometer, and this is an outside micrometer, and it's based on a screw thread mechanism. When you turn this thimble, the shaft moves in and out, and you can read the numbers off the barrel. This particular one is accurate to 1/10,000th of an inch, and it's repeatable. These gauge blocks, however, are accurate enough to allow us to standardize this and make sure that it's reading accurately. There's something else we'll use on the 3D printer is an inside micrometer, and it's the same screw mechanism, and as you see, as it unscrews, it gets longer. As it screws in, it gets shorter, and you read the numbers off the barrel in the same way. We'll use this to make sure that the nozzle on our 3D printer is absolutely level. Now, for 90-degree corners, we have a couple of choices. We have the traditional combination square or machinist square that allows us both to measure, to have a straight edge, measure straight things, but to measure 90-degree angles. So if I want to test a part, I just slip it in here, and then I apply the light test. Do I see any light at the corners? Because if it's not square, for example, if I tilt it off, you'll see light on one edge or the other. So that's one way of getting a corner. Another more standardized approach is something called a 1, 2, 3 block. And here's a block that's exactly 1 inch thick, 2 inches wide, and 3 inches long, but it's prepared to have very accurate 90-degree corners, which will come in handy as we'll see. Now the straight edge, as I mentioned, if I just want to use this as a straight edge, and I take another object that I think is straight, a 1, 2, 3 block should be straight, and I hold this between, and you can hold it up to the sun even if you like, I don't see any light between those. That's a good check to make sure this ruler is still straight. Now, here's where it gets interesting, where you start using the combination of all these tools to achieve the result. If you want to measure an angle, that is a portion of a circle, you use something, or if you want to test an angle that's been prepared, you use something called a sine bar. And all this is a piece of hardened steel with two rollers exactly, in this case they're exactly 5 inches apart, okay, so that if I lay it flat on a flat surface, this surface is at 0 degree angle. In other words, it's parallel to the base. So I could test that, but I won't just now. But if I want to create any particular angle, all I have to do is lift up one end by a known amount, and then I can use a little trigonometry to find out exactly what the angle is. For example, if I put a 1.5 inch block under here, you can see that because it's round, it rests at only one point, and this angle here is going to be 90 degrees, but this angle is dependent only on how far I raise that block. If we recall our discussion of the Egyptians and the 1, 3, 4, 5 triangles, what if I set this on a 3 inch block? Now I have a 5 inch hypotenuse, a 3 inch vertical, and a 4 inch base, and now I know that this angle is going to be a little over 36 degrees, for example, and that can be a way to test a part that has to be at a particular angle. It can also be a way, if I need to make a part for my 3D printer or any other machine, I could clamp this at this angle. I could clamp a unprepared part and then machine that part away to exactly that angle. Okay, so that's called a sine bar. And let's just go ahead and test that with a last thing we want to test is parallelism. And here, this little round dial is called a test indicator, and each mark on that dial is 1/2 thousandths of an inch. So with this, if I slip this bar under here, and I see where the needle is, and its relative measurement, so it doesn't matter, you can see as I slide this around, it vibrates a little bit because of dirt and whatnot, but it stays the same, which proves to me that my base, or this piece of metal, is indeed parallel to the base. Now, last tool that can be used to evaluate parts of machines or make machines is V-blocks. And a V-block is simply another piece of hard steel that's got a V-shaped groove cut into it. And for example, if I have 2 of these, I can evaluate a round. It will hold this round object very securely, and in fact, if I'd like, I can clamp it in here to make markings or carve various shapes out of it. But if I just want to confirm in a quick way, it's not a perfect confirmation, but if I want to confirm that it's round, I can take my test indicator here and place it on top, so that there we go. So when I rotate it, that will tell me if I have any bends in my rod, and I can see I might have a 1/2 thousandths of an inch bend in this particular rod. It's been kicking around in the shop for a while, but that's a way to evaluate whether or not you've got parts that are straight enough. If I actually, let me show you how to use this. If I actually want to find out the diameter of this rod at any one point, I place it in here, and I turn the screw until it clicks 3 times, take it out, and I get my reading. I'll take a look here, and in fact it says 3.3, it's 0.315 thousandths of an inch, which is indeed what it's supposed to be. However, that of course is no guarantee. That's at one point. If I turn it around and measure the diameter again, it might be different. If I move down here, it might be different. So there are, we haven't yet proven that it's completely round, but it's good enough for the purposes that we need it for. Now, of course, an earlier way to test for roundness is to take an object and put it on a flat surface. Now, this particular flat surface, I know this table is not level. Does it roll freely? Once you start it, does it keep rolling? And you can see that if you have a very small angle of inclination, you can determine whether objects are round based on how high that angle has to be before it starts to roll. In fact, that's how they used to test shotgun pellets, for example. After they were prepared, they would put them on an inclined plane and determine whether or not they were round based on whether they rolled off or not. So that's a real quick review of the very simple hand tools that underlie the precision that is built in to almost all of our modern machine tools. Now, let's take a look at a part of a 3D printer. This is an aluminum extrusion. That's a standard part, and let's say that I want to find out whether it is cut square. In order for it to make a nice square base for our machine, I'd like it to be cut squarely, and I can already see that it wobbles a little bit. But if I take, for example, my 1, 2, 3 block with a perfect 90-degree angle and hold it against it, I can see that it's not perfect. It's probably about 1/100th of an inch out of square on that side. The other side seems to be perfect. So what that tells me is that one end has a 90-degree angle, the other does not, and it might need to, if I were going to assemble this into a very precise machine, I might have to clean up that angle with a grinder to make sure that it was actually 90 degrees. Now, let's pause. Now let's see how one of these tools can actually be used to determine whether the bed of this 3D printer is indeed level with respect to the height of this nozzle here. And to do this, one quick way is to take the gauge block that I assembled, and I just happened to set it at 1.5 inches, which was close to where it was, and I turned this down until it just touches. And you can just hear it kind of scrape by the bottom of that aluminum housing. So it just touches there, and now I'm going to see if it touches. It should touch in the same amount every place else. Here, I can see light between them. It doesn't touch at all. And if I move over to this corner, I can see I can't fit the gauge block underneath. So that tells me that it's high on the right side. If I go to the center, it's low. The center is low in this case because the gauge block does not slip under it. The right side, the center is high. The right side is low. And if I go all the way back, I can see this whole side is low relative to the center. And if I go over to the right side, can see over there that it actually bumps the base. So that tells me that I need to lower that by a certain amount to have it level. And then after I adjust these screws on the base to pull down the two parts of the base, I retest it until it has exactly the same fit under the nozzle housing. If you have a standardized item like a gauge block that is known to be accurate within so many millionths of an inch, you can use that, as I said, to calibrate your other tools. And if you're going to be using the tools to measure the quality of parts, for example, this 3D printed box, you want to make sure it's absolutely right, because sometimes portable tools will get out of calibration. And the way you do that is, for example, with a 1-inch gauge block, I put it in here and adjust it until the micrometer faces contact it, and I see indeed that it comes out to be exactly 1 inch to within 1/10,000th of an inch. So it doesn't need to be calibrated. And now I can be confident that if I use it to measure the distance to one of these corners, it's going to be accurate and consistent. Now, I did one face. The other one, is loose. So that tells me that I've got a few 10,000ths of an inch, maybe a thousandth of an inch difference between one edge of this cube and the other, which is why I printed a test block in the first place. This one is also loose, and this one is just right. So 2 out of the 4 sides are the same. The other 2 aren't, and that's why this the 3D printer required additional calibration. Now, one other test that you do on parts like this is, are they square? And we're going to use the light test. I'm going to place the one edge of the block here and see if we see any light. And I think you can see against the white background that indeed those sides are not straight. They look a little bowed. There's light on either end. Let's turn around and check this. That looks like it's just a tiny bit off. It wiggles against the bar. So those faces are a little bit rounded. And that side, same thing. So that this test told me, with just looking at the straight edge, that this surface is a little bit rounded. And that's probably because I polished them after I printed it to see what kind of surface it had. And the polishing operation introduced some curvature, which was unintended. The last thing I want to show you about the process that leads to manufacturing machine tools is, how do you decide where to cut something? And this uses a combination of 3 of the tools we've looked at: the 1-inch gauge block in this case, the surface gauge, which is really just used for marking, and we're going to use this to make a mark at exactly 1 inch. And once we've established that this side is square, we know this is vertical. So what I do is I set this by adjusting the screw threads on the surface gauge so it just barely touches the top of this 1-inch gauge block. And then I know that the very sharp point of this scribing tool is exactly 1 inch, and all I have to do at this point is hold this down and make a little mark like this. And I think you can see, if I hold the light, the scribe mark is right here, and I can use that as a guide if I need to machine a groove or make any alteration that has to be exactly 1 inch, plus or minus a couple of thousandths of an inch, which if I were just going to, take an ordinary ruler and say, all right, make that mark at 1 inch, if you're doing it by eye, it's extremely difficult to see where that mark is. And certainly you don't want to use something like a pencil, because the width of the pencil mark is way bigger than the accuracy that you need in assembling this tool. Well, thank you very much for watching.